So we've now filled out the easiest 5 out of the 9 cells in our table. We've seen that finding the y-intercept is easy in any format. We just plug in x equal to 0. We've seen that vertex form is built specifically to help us find the vertex. We've seen that factored form is built specifically to help us find the roots. What we'd now like to do is fill out the remaining 4 cells in our table, the slightly difficult ones here. The first one that we're going to go ahead and take a look at is finding the roots when we're in vertex form here. This one, it doesn't necessarily require a special concept, but it does have a little bit more of an algebraic challenge than some of the others. So we are going to look at a good spread of 4 different examples here to make sure that everybody sees all the different things that we would like to consider. Let's start with what I think is going to be the easiest example. The good news here is that when we're looking to find the roots in vertex form has the very special scenario, and that is the only format in which there is a single instance of x. Factored form has 2 different x's in it. Standard form has both an x and an x squared in it. This one's special because since there's only one instance of x, we should be able to solve for it. When we're interested in x-intercepts, also known as roots, x-intercepts always occur when y is equal to 0. So in this example here, we're going to go ahead and set y equal to 0 and simply solve for x. It's going to take us a few algebra steps, but there's nothing special about them. We're simply unwrapping the operations that are surrounding x until x is alone. So let's go ahead and do that now. We're going to set y equal to 0 because we're looking for x-intercepts, and x-intercepts always occur when y is equal to 0. And now we're just solving for x. So let's start unwrapping the operations that are surrounding x here. First, I'm going to go ahead and add 27 to both sides. Next, I'm going to undo any multiplication or division, so I'm going to divide both sides by 3. The next step is to undo any exponentiation. Here what we'd like to remember is that to undo squares, we use square roots. The small piece of information that's very important here, lots of students often make the small mistake here, is to remember that we're asking a broader question here. We squared something and we got 9. What number could we have squared to get 9? Well, it's really important for us to realize that there's 2 different answers. I could either square 3 or I could square -3 to get 9. What we want to remember here is that when we take a square root on both sides of an equation, we always need to introduce a plus or minus to remind ourselves that we're not sure if we squared the positive version or the negative version of a number to arrive at the value of 9. So here I'm going to give plus or minus the square root of 9 as my new value on the left, now that we've taken the square root on both sides. And the square root of a squared term should simply be the terms on the inside here. Square rooting and squaring are inverses, they've canceled away. I know that the square root of 9 is 3 in this case, so I can rewrite this as plus or minus 3 equals x minus 5. And finally, to wrap up solving for x, I'm going to go ahead and add 5 to both sides. Finally, what I'd like to do is state this in a bit more of a sensible statement right here. When I see the statement x equals 5 plus or minus 3, what I know is that this is really going to lead me to 2 different roots. One where we use the plus option, one where we use the minus option. When I add 5 and 3, I'm going to land at the root of x equals 8. When I subtract, when I do the negative route here, 5 minus 3 is going to leave me at the root of x equals 2. So these should be the 2 roots that we're going to arrive at in this scenario here. So what we've seen is that to find roots in vertex form, all we want to do is set y equal to 0 and solve for x. It's always going to take us a few algebra steps. In this case, I've set our numbers up so that things work out relatively nicely for us. Let's go ahead and take a look at a couple other examples here and see some other things that we might expect to see. This next example should be very, very similar to the last. We're just going to have some less comfortable numbers to work with here. Things just aren't going to pan out so nicely as they did last time. Again, to find x-intercepts, we set y equal to 0. And whenever we're in vertex form, we always have one instance of x, so we can directly solve for it. The first thing I'll do, just like in our last example, is I will undo the addition or subtraction on the end. Here I'm going to subtract 6 from both sides. And now I'm going to undo any multiplication or division. In this case, I'm going to multiply both sides by -2 to cancel the -1/2. Multiplying the left by -2 is going to give me a +12. Multiplying the right by -2, the negatives will cancel. 2 times 1/2 is 1. So I'm multiplying by -2 because that's the reciprocal of -1/2 here. And I'm going to land at x plus 2 squared. Again, our next step is to undo any exponentiation. Here I need to take a square root, and I want to remember my lesson from the last time. Anytime we take a square root on both sides of an equation, we always need to include a plus or minus to reference the fact that we're not sure if we squared the positive version or the negative version of a number to arrive at the value on the left side of 12. So I'm going to give plus or minus the square root of 12 is what's going to be on the left when I take my square root. Taking the square root of a square on the right should just leave me with the remaining terms on the inside. Finally, to continue solving for x, I just need to subtract 2 from both sides. And so I can report my final answer here as -2 plus or minus the square root of 12. In this case, I don't really have a much better way to write my answer. The square root of 12 is never going to be a very nice clean number for us. Like last time we had square root of 9, that's just 3. Well, here we don't quite get that. In this case, I think it's pretty acceptable for us to leave our final answer in this form right here. But don't forget, this is equivalent to us writing our plus route and our minus route as we did before. If you would like to write this out as 2 different roots, then we can see that one of our roots is going to be located at -2 plus root 12. Our next root is going to be located at -2 minus root 12. You should compute both of these values in your calculator and then verify that these are the 2 decimal valued roots that you do see when you look for your roots in Desmos. One last thing I'd like to say about this example is that you should notice that I will be asking you things on our upcoming test, for example, that will say things like, tell me the exact roots associated with something perhaps in vertex form here. Well, when I say exact, what I mean is I do want things in terms of the square roots, not necessarily just the decimal values that you get out of Desmos. So be aware that I do want us to be able to do these algebraic steps, not necessarily just get out a decimal value for the roots. We'd like to be able to state the exact roots of this quadratic here, and we see them as -2 plus or minus the square root of 12. So in this example, very similar to the first, our only additional challenge here is to recognize sometimes the square root's not going to come out cleanly. That's fine. We can still reference this square root term within our solutions out here, whether it's got the plus or minus in it, or whether we state 2 individual solutions, one with the plus and one with the minus. Let's go on to our third example now. In our third example, we should see that this only mostly looks like we're in vertex form here. The thing that we're missing is it seems like there's not a term on the end. But just remember, anytime that we're sort of missing an additive or subtractive term, you can always think of that as like a +0 that sits out there on the end. It might be helpful, by the way, for us to think for a moment that this is a quadratic that opens up. The parabola will open up, and it looks like we have a vertex location at +3, 0. We'll come back to that as a graphical idea here in a minute. If I'm going to identify where are the roots in this vertex form equation, we can do the same thing as we've been doing. X-intercepts occur when y is equal to 0. And since vertex form always has only one instance of x, we can immediately solve for x. Here I don't have an addition or subtraction step to undo, so I'm going to first undo my multiplication or division step. That's not a very exciting thing to do here because the first thing I'm doing is dividing by 2 on both sides of the equal sign. 0 divided by 2, that just stays 0. On the right, when we divide by 2, we cancel off the 2 that's sitting in front, and we get x minus 3 squared. To proceed on in the same fashion as we have in the previous videos, we would now go ahead and take a square root on both sides, and we would recall that we always want to keep that plus or minus whenever we take a square root. However, notice in this case that that doesn't really seem to be that helpful of a statement for us. This is a kind of ridiculous expression that we've got over here on the left. 2 reasons. 1, the square root of 0 is just 0. 2, plus or minus 0, well, those are the same number, right? There is no sensible way to attach a sign to 0. So the reason I want to bring this example up is because it looks like when we wrap up solving for x here, it looks like there's only one root. Now, we talked about this in class. We like to think to ourselves, I've asked this question, how many roots in general do parabolas have? And the simple answer that students often like to give me is 2. Lots of times parabolas do hit the x-axis 2 times. We're seeing here, though, that's not always the case. Here we're suggesting that there's only one location that we've hit the x-axis. And in a sense, we kind of identified that information at the beginning of this problem. If we think about what the graph of this parabola is going to look like here, we've identified a few things from the get-go. Since this is in vertex form, I can identify the vertex is located at positive 3, 0. So positive 3, 0 is going to be sitting here. We can also see that this parabola should open up and be slightly narrower than a traditional parabola. So I'm picturing a graph that looks something like this. What we can see is that because this parabola is sitting right on the x-axis, it's in a sense sort of like where there would be 2 roots, those have come together to be 1 root that is maybe repeated at the x value of 3 right here. So notice that sometimes we don't get 2 answers. When we're looking for roots of parabolas, I think that most students expect to see 2 solutions, but it's possible to only see 1 root on any given parabola if that parabola is sitting right there on the x-axis, whether it opens up or opens down. It could be one of these touching roots where we just come down and touch the x-axis and then remain on the same side. We'll discuss quite a bit more of this next week when we talk about higher order polynomials as well. Let's look at one last example. Finally, let's find the roots of this given parabola here. Again, roots occur, roots are x-intercepts. X-intercepts occur when y equals 0, so we set y equal to 0. And since we are in vertex form, there's only one instance of x, so we can directly solve for it. So I'm going to perform my first step as usual, adding and subtracting the additive term on the end here. I'm going to get a negative 3 on the left. Again, I'm going to undo my multiplicative term here, my a term of 1/3. I can undo multiplication by 1/3 by multiplying by 3 on both sides to cancel this. So I'm going to land at negative 9 equals x minus 2 squared. And now we have to ask ourselves, if I squared a number and got negative 9, what number did I square? Well, you should have a bit of a problem coming up with that number. One thing that we know about squaring numbers is that anytime you square a number, it becomes positive. A negative times a negative is positive, and a positive times a positive is positive. So it seems a little confusing to me as to how can we end up with squaring a number and getting a negative out. It doesn't seem like this ever happens. So what's going on here? Did we do something wrong? Well, again, let's think back to the easy information that we know. Anytime you ever see a quadratic in vertex form, you should immediately be thrilled that you know an easy piece of information, where the vertex is located. Notice in this example right here, we can easily see the vertex location of positive 2, positive 3. So I'll say here our HK location is positive 2, positive 3. So if I were to go begin and attempt to graph this quadratic, I could go to positive 2, positive 3, and I think that that's going to be the vertex location. The other easy information that we can see graphically is that the a term is positive. This suggests to us that the parabola should be opening up. We can also see from the 1/3 that this should be a wider than usual parabola. So if I'm drawing an opening up wider than usual parabola that has a vertex of 2, 3, here is what my approximate graph might look like. The hopefully obvious graphical thing that you can see here is that this parabola does not have any x-intercepts. Because the vertex is located above the x-axis and it opened up, we're never going to actually hit the x-axis. That's why algebraically we ran into an impossible algebra situation over here, because it was representative of the fact that our graph does not in fact hit the x-axis and we were looking for x-intercepts. So be aware here that sometimes parabolas have no roots when they are either above and open up or below and open down the x-axis. In our previous example, we saw that sometimes parabolas have 1 root when they're sitting right on the axis. In more traditional cases, we often expect parabolas to otherwise have 2 roots. So just be aware that any of those 3 scenarios can happen whenever you're searching for the roots of a parabola that is in vertex form. So now we've looked at a few examples, and what we've seen is that to find the root location for a parabola that is in vertex form, we don't really have any specialty techniques to do. We simply want to do the algebra. We know that roots are x-intercepts. We know that x-intercepts occur when y is 0. And the thing that we like a lot about vertex form is that there is only one instance of x within vertex form, which makes solving pretty easy. So our instruction here, sometimes it may take a little bit of work, but the instruction itself is not conceptually difficult. Set y equal to 0 and solve for x. As long as we can solve for x, remembering that we're always going to have to take a square root and introduce a plus or minus, then we can find the roots in vertex form. This is actually going to be a key for us for figuring out one of our last and most important cells in this table. Now that we've walked through a few examples of finding the roots in vertex form together, you should go ahead and do a few on your own. Here's 3 examples of a parabola, a quadratic that is in vertex form. In all 3 cases, you should try to identify the roots if they exist. It might be, as we've seen, that there are either 0, 1, or 2 roots associated with any of these equations here. So for each of the 3, attempt to solve for the roots, then go to Desmos, graph the parabola, and see if it has the same roots as you have found algebraically. Remember that I am interested in giving exact answers for roots in case they include square root terms, but remember that Desmos is always going to give you decimal values. So if you get any answers that include square roots in them, go ahead and compute what the actual answer would be by going to your calculator. I think we saw one earlier that was something like 2 plus or minus square root of 12. You can throw statements like that into your calculator and get the decimal to verify that it's going to match the decimal that you end up seeing in Desmos. Finally, I'd just like to say, I think that this is definitely one of the categories that requires a little bit of practice. Make sure you try a couple of these. These do have quite a bit more algebra steps than some of our other operations do, so make sure that you're comfortable with the steps that are involved here.